Okay, let's discuss the path planning algorithms now. What we've seen here is there are simple algorithms, they're not very complex, and I'm going to just give you a quick description of each to show how the accomplishment of the task was done. So let's look at the first one here. We have algorithm for visiting stationary targets. What we have here is, first of all, the UAV, upon start of simulation, will calculate the Euclidean distances to each target, and then it will create the path based on the closest target. So that's what we see in D bar. So first there's a calculation of Euclidean distance, then organization in terms of increasing distances in D bar, and then for the test itself, first of all, the UAV will hover for 20 seconds. Now this is done for stabilization because let's not forget, during all these tests, we have the UAV at a height of 0.6 meters, and this is not changed. So we wanted, first of all, to get to this height without any perturbation, so we don't skew the results. And then we wanted to, for the next 20 seconds, get to the next target, the closest one, then move on to the rest of them and return to its initial position. So this is what is described in this algorithm here. If we move to the second one, algorithm for following a moving target. So here what we've done is, again, there's a 20-second stabilization time, and after that the UAV will locate the moving target in the area and will follow it. So that's what we see with desired XY of the actual UAV is equal to the position of the moving target in the area. Now the details of this will be discussed further in the results. For the algorithm for following a predetermined path, in here what we do is we have a set of coordinates in P bar, and we feed those to the vehicle every 20 seconds. So again, we do have the stabilization time, and then we feed each one. Every time the UAV gets to its new position, it will carry on to the next set of coordinates. For the facilities inspection here, it was a bit more complex because we've done two tests. One is for encirclement of the target. What I mean by this is the vehicle or the UAV itself will encircle the robot in the center, and it's mounted with the UAV itself is mounted with a camera. So first of all, we encircle the target to get some sort of exposure to the robot being inspected, while in the second test we took user input. So we had the user himself determine different Cartesian coordinates in order to have the best camera angle. So now that we've discussed the problem formulation, let's look at a bit of the results. So how all of this fits together and if we've been successful in our proof of concept in small lab environment. We'll start first with the stationary targets. We've completed two tests. So we'll look at the first one. What you're looking at here is a Cartesian representation of the area. In other words, it could be, it's a snapshot from above. Now, what you have here is the purple diamond represents the Q-wall X4. The green, blue, and black diamonds represent the targets that are used. The solid red line is the vehicle path, or the UAV path. Now you can see here that the purple diamond, it starts at -1 and 1, and it will reach the green one, which is the closest, and then carry on to the rest of them, the rest of the targets. The UAV is successful in accomplishing this. So the main requirement for visiting stationary targets is the UAV is successful in locating those targets and then moving on to the next one. And we can see that the vehicle is successful in this case. If we move on to the second test, the main changes are different positions for the actual targets, and we can see that once again the Q-ball X4 is successful in reaching those locations. Now you're probably wondering why the red path or the UAV's path is not straight. I just want to remind you here that this is not a ground vehicle, this is a flying vehicle, so there is some sort of ground disturbance that's caused by the adjacent walls in our lab environment. So that's why you see a bit of a skew going from the black target to the initial position at the end of the test. But overall, you can see that the UAV is successful in reaching those locations and returning to initial position. So the stationary target test is successful. If we look at moving target now, what we've done here is we've taken a Husky robot by ClearPath Robotics, and this is in our lab environment. And what we've done is we've used this as the moving target. So this represents kind of your haul truck or your LHD moving around the area. So here we took a snapshot of the actual test. Now you can see the green mat holding the trackable so that we can locate the Husky in the area. You can also see the UAV successfully following its target in our little environment. Those are the walls that kind of cause a bit of wind disturbance while flying. That's why sometimes we have a bit of an increased error in certain locations of our testing. And we can see here one of the two tests for following a moving target. So again, the purple diamond represents the Q-Ball X4. The green here represents the Husky robot. The blue is the vehicle path. And we have here the red path, which is obviously the UAV path. Now, the UAV is successful in following the moving target. There is a bit of an error of less than 10%. This is normal for any real-world implementation, as we have here. But overall, you can see that the data we've picked up here can be used by engineers to minimize the error. Going back to some of the examples that we've done in this course, where we're always trying to look at the error and trying to minimize it as much as we can. So as an engineer maybe working in a mine, you can take this information and see if your vehicle is actually following its correct path around the autonomous mine. Now, I included this test specifically in the project and the presentation for what you see in the bottom left. So again, the purple diamond represents the Q-Ball X4, the green is the Husky, and the same paths. Now, what you see in the bottom left, the vehicle did not actually exhibit this behavior. This was simply loss of localization using the GPS system. So the reason why I included this here is to show the viewers that when using complex systems, you're going to have problems where you lose localization, and the vehicle needs to be able to make a decision on that. So what happened in the lab is the vehicle did not actually exhibit this, but it was able to continue its path and actually follow the desired path either way. So in any real-world implementation, I invite the engineers to always have a plan B, in other words, where if there is loss of localization, the vehicle is able to either go back to home station or to its initial position, or to adjust to the changing environment as need be. So this was the main reason why I included this test here, just to show the complexity of using these systems. Now, looking at the pre-planned path, here again we have the purple diamond following the blue path. We have a bit of an overshoot on the sides at -1 and 1 and almost 1.2 and 0, and this is due to the sudden change of direction. The low-level PID takes a couple seconds to actually reach steady state, so that's why we have a bit of this skew there. But overall, you can see that the vehicle is successful in following this path, and the importance of this is to be able to take pictures at this specific frequency for mapping or for photogrammetry. So this is how we see the test was actually successful. Now, looking at facilities inspection, at first for my problem formulation I included only the 3 tests, but then with added time I thought to include something even more interesting. So what I did here was I took the TurtleBot by ClearPath Robotics again in order to inspect it. So this was the object of our inspection. Now, we ran 2 tests as I highlighted before, which is going to be the facilities inspection, where there's an encirclement test and there is also a user input test. So for the encirclement test, here we have the TurtleBot represented by the orange diamond, and we have the UAV, which is following the blue dashed line, which is the ideal circle of radius 1. There is a bit of an overshoot in the beginning in the UAV's path, and this is due simply because it's trying to adjust height and its Cartesian position at the same time. I wanted to highlight throughout these tests that the height is maintained at 0.6 meters, and the yaw angle is maintained stable also. Now, this will be reflected a bit more in the results. We'll highlight further. But other than that, we're just playing on the Cartesian coordinates, x and y. But you can see, despite a bit of an overshoot in the beginning, the UAV is able to maintain its path and get to steady state quite well. This is using the model predictive control algorithm. And if there are any questions about how this has been done, please refer this to me at the end, and I can refer you to the paper that I've used to accomplish this. Now, 2 videos actually have been completed for each for both tests. They're of 1 minute 40 second length, and I've included those later on. And I've taken the best snapshots of exposure of the actual robot, and this is what we see in the next one here. So this one is from the encirclement test. Now you can see the actual turtle bot there. Please excuse the carbon fiber frame, and this is because of safety, as I mentioned before, but you can clearly see the robot itself. You can see some of its features, such as the Connect and the laptop that's on the bottom there. Now, this picture was the best one from this test, and you cannot see a full exposure of the whole robot. So for the user input test that we see here, we do have a full exposure of the actual turtlebot here, and we can see the Connect, and we can see other features that are available there. So this is the test where the user chose the coordinates in order to have the best camera angle, and both tests for the facilities inspection were successful. I've included this here in order to reflect what has been done by Cyber Technologies with the Montara oil platform that I've highlighted in the introduction section. So you can see that both tests were quite successful at capturing an accurate image of the turtlebot. This concludes the results. And again, if you find that these were not detailed enough, or if you have any questions, please include that in your peer evaluation or in the notes section. And I may provide more details or more results, because all of this is still available. Now, to conclude, I would like to thank you for tuning in. My name is Mohammed Skandarani, and what we've done here is using UAVs in open pit mining applications. We've taken simple applications such as photogrammetry, aerial photography, and the facilities inspection, and applied them in a small lab environment as a proof of concept. Now, these tests were successful in rendering good results, and as a conclusion, I just want to invite you to check out the full robot inspection videos at the links posted in the notes section. So in my YouTube channel, I included the videos where I took the snapshots during facilities inspection. You're welcome to scroll through those and check them out. So again, thanks for tuning in, and I hope you have a wonderful day.